Hello everyone, and thanks for watching Edupedia World videos. In this video we learn about the kinematics of circular motion, which is another type of motion in a plane. So we've all seen circular motion in our daily lives. We'll assume a particle is moving along a circle of constant radius, and the first thing to know is that circular motion is always accelerated. Because even if the speed of the particle is constant, that is, the particle is covering what we say equal angles in equal intervals of time, the magnitude of the velocity is constant, which is the speed, but the direction of velocity is always changing, right? So you can see that at this point, the direction of velocity is vertically upwards. At this point, the direction of velocity is upwards and towards the left. The direction of velocity is downwards and towards the left, it's downwards and towards the right. In fact, at any point, the direction of velocity is at the tangent towards the circle, right? So any point you can draw the tangent and it will give you the direction of velocity. If the body is moving along a circle with constant speed, that is, it covers equal angles in equal intervals of time and its speed is not changing, then we call it uniform circular motion. Remember that uniform circular motion is always accelerated, unless of course the speed is 0, because if the particle is moving along a circle of radius 10 meters with a speed of 20 meters per second, the direction of its velocity is always changing. So the particle is accelerating, and by Newton's second law, a force must be acting on the particle. But that falls under dynamics of circular motion, and we'll see that after we've covered Newton's laws. The direction of acceleration is the most interesting part of circular motion, and it is always towards the center. And we can almost see that. For example, let's consider these 2 points. At this point, the velocity is upwards and towards the left. Here, the velocity is downwards and towards the left. So, between the points, the acceleration or the average acceleration would be the change in velocity divided by the time. So, the direction of the acceleration is always the same as the direction of the change in velocity. And change in velocity is simply final velocity minus initial velocity. So if we use these two events, this is the final velocity and this is the initial velocity. If we wanted to subtract the initial velocity from the final velocity, we would do this vector minus this vector, or this vector plus the opposite of this vector. The opposite of this vector would point in the opposite direction, which if we translate to this point would point something like this. And we can sort of see that their sum does point towards the center. I'll prove the direction is always towards the center rigorously in a moment, and we'll also see what the value of the acceleration is. So let's say a particle is moving along a circle of a constant radius r with a constant speed v. Speed, remember, the speed is constant. The velocity by definition has to change if the direction is changing. So I'm going to take a small part of this circle and I'm going to enlarge it. So this small part, let's call this angle theta, and apologize you can't see here, but let me enlarge this. So that small part would look something like this. At this point, the velocity would be towards the tangent and the speed would be v. Here the velocity would again be towards the tangent and the speed would be v. Let's call this angle theta. And let's just draw a straight line, the construction. So since this angle is theta, and these two angles are equal, keep in mind this is the radius. We'll use a little bit of high school geometry now. These two are the radius which are equal. So these two angles must be equal, right? Since this angle is theta, this angle plus this angle makes 90 degrees. So the sum of these two is 180 minus theta. And if you divide it by 2, each of these angles will be 90 minus theta by 2. Half of 180 minus theta. And since this total angle is 90 degrees, this little angle becomes theta by 2. Right, this small angle is theta by 2. Similarly, this small angle is theta by 2. So hopefully the geometry is clear to you. Now, what is the change in velocity? we'll take two directions. We'll call this our x-axis for the moment and this y-axis. Right. So we see that the x component of velocity initially is minus v cos of theta by 2. Minus because it's in the negative direction. Similarly, the x component of the final velocity is minus v cos theta by 2. So we see that the x component of the velocity is not really changing. So we'll write this. V initial, I'll just call it u for now. I'll just call it v initial actually. U is referred for something else. V initial x is equal to minus v cos theta by 2. V final x is equal to minus v cos theta by 2. These two together imply acceleration in the x direction is 0. V initial y is v sine of theta by 2. If you're not familiar with taking components, I suggest you look at the video on vectors once again. And v final of y is the negative of this. It's minus v sine theta by 2. So the change in velocity, we need to find out the acceleration in the y direction. That is change in velocity by time. Change in velocity is final minus initial. So minus v sine theta by 2 minus v sine theta by 2. So we get minus 2v sine theta by 2. This is the change in velocity divided by the time taken. Right. Now how do we calculate the time taken? If the speed is v, the total time taken is 2 pi r by v. And that this is the time taken to cover 2 pi radians. So to cover theta radians, we'll simply multiply by theta by 2 pi. So that gives me theta r by v. So instead of t, I can write theta r by v. Now I'm going to use a little bit of trigonometry. We've seen that when theta is very, very small and measured in radians, that is when theta goes to 0, limit theta goes to 0, sine theta by theta equals 1. And this is sine of theta by 2 by theta by 2. We can take this 2 downstairs and write it as theta by 2. So sine theta by 2 is approximately equal to theta by 2, because remember I have taken theta to be very, very small. This is an enlarged figure of this, and the closer I take theta to be, the closer I get towards instantaneous acceleration. So these can cancel, and what I am left with is ay equals minus v square by r. Minus is just to denote the direction because we took the upwards direction to be positive. Ignoring the minus, we could write it in a better way as the acceleration. I'm going to write it as r to refer to it as the radial acceleration. The other acceleration is tangential, which we'll see in a moment. So acceleration radial, the magnitude is v square by r, and it points towards the center. We can see that the negative y direction is towards the center. So I've derived this result, which is a very important result and which you will use over and over again in problems involving circular motion, that whenever a particle is moving along a circle at a speed v and the radius of the circle is r, the radial acceleration, that is the acceleration towards the center, is equal to v square by r. Right. Now, what if the particle is moving, but it is also changing its velocity? So let's say the particle is moving in a circle of radius r, but with a speed v that is changing. So if v is a function of time, let's say, that means initially it's going down slowly and it's accelerating and its speed is increasing as a function of time. In this case, the particle has two accelerations. There is the radial acceleration, which is v square by r, towards the center. And this is always true. Whether the particle is moving with this constant speed or variable, at any instant of time, it will have an acceleration equal to v square by r towards the center. Now if it's moving with a variable velocity, there is another acceleration which actually measures the change in magnitude of velocity. You could sort of think of the radial acceleration as measuring the change in direction of velocity, and the tangential acceleration as measuring the change in magnitude of velocity, which is the change in speed. So if the speed is not changing, the tangential acceleration is 0, but if the speed is changing, the tangential acceleration is simply what we know and love, dv by dt, and this acts tangentially. Right, so the particle has a radial acceleration, and it also has a tangential acceleration. I'll call this AR and I'll call this AT. The net acceleration is obviously the vector sum of the two, and since these two are in mutually perpendicular directions, the direction towards the center is always perpendicular to the tangent. That is actually the definition of a tangent. So actual A is root of AX square plus AT square, that is V square by R whole square plus dv by dt whole square. I'm using the law of triangle rule of addition, and the angle between them is 90 degrees, so cos theta is 0. We could also try to find the angle of the acceleration with the tangent or the radius. This will be the net acceleration, and it will make a certain angle with the tangential direction, and it will make a certain angle with the radial direction. If I call that theta, tan theta will be acceleration tangential minus acceleration divided by acceleration radial perpendicular by base, which will simply be dv by dt divided by v square by r. So how do we use these in problems? Let's say somebody says to us that a particle is moving on a circle of radius 10 meters with a speed changing with time as 2t plus 5 meters per second. And we are asked the acceleration net at t is equal to 3 seconds. So we need to find out the radial and tangential accelerations. The radial acceleration is simply v square by r. At t is equal to 3 seconds, v will be 2 times 3 plus 5, that is 6 plus 5, that is 11. So 11 squared, 121 by 10. The tangential acceleration will be dv by dt, which is 2, and that is constant. You can see dv by dt, derivative of 5 is 0, derivative of 2t is 2. And the net acceleration will be root of 4 plus 12.1 whole square. And you can simplify this to whatever it comes out to be. So these are the two things we've learned in this lecture, tangential acceleration and radial acceleration. There are certain number of other concepts which are important, which are related to how we measure things in radial and tangential motions. So when we analyze circular motion, we generally don't talk in terms of speed or in terms of displacement. It's much more convenient to talk in terms of angles. So instead of measuring displacement by time, we measure angular displacement or angle by time. So again, this is an enlarged figure of a random circular motion, and the particle goes in this direction. Of course, it covers the complete circle as well. So let's say this time interval is delta t, and let's call this for the moment as delta theta, the change in angle. It could be measured from any particular angle value. So if the particle covers a distance, an angular distance or an angle of delta theta in a time interval of delta t, then omega is called the angular velocity. And omega has a magnitude is equal to delta theta by delta t. And now we are going to see a lot of analogies between this and what we learned in kinematics. This is delta t. So this is the average acceleration between two time intervals. So this is average. If we want to find out omega instantaneous, I think you might have guessed it, it would simply be d theta by dt. Similarly, alpha is the angular acceleration. And alpha average is change in angular velocity by time. And alpha instantaneous is equal to d omega by dt. Another thing we see, now I'm going to really show you the power of mathematics in science. Why do we choose to represent everything in terms of mathematics? Because we can use similar mathematical structures for completely different physical quantities. So we've seen that v equals dx by dt and a equals dv by dt. And in that case, for constant acceleration, we get three particular equations of motion. Similarly, if the angular acceleration is constant, we get three equations of motion, which I'm going to write now, and you can try to derive them at home. The equations of motion are omega is equal to omega naught plus alpha t. Omega naught is the initial angular velocity at the initial event. Omega is the final angular velocity. Theta is equal to omega naught t plus half alpha t square. And omega square is equal to omega naught square plus 2 alpha theta. These are exactly the same as the kinematical equations, except v is replaced by omega, u is replaced by omega naught, a is replaced by alpha, and t is the same, and s is replaced by theta. Right? So these are the standard equations which we can use. So we can be given that the initial angular velocity is 10 radians per second and the angular acceleration is constant in 2 radians per second square. How much angle does the object cover in 5 seconds? Something like that. Again, these are only valid for constant alpha. But since just like we know how to calculate motion for variable acceleration, we know how to calculate things for variable angular acceleration. For example, if I've given that theta is 2t cube plus 3t, then omega will be d theta by dt, that is 6t square plus 3, alpha will be 12t. So this is exactly analogous to everything we've done in kinematics. One last thing left, that is the relationship between linear and angular variables. So we do know the definition of the angle, right? If this angle is theta, all we need to do is draw an arc with a constant radius, and if this length is L, theta equals L by R. So d theta by dt equals d of this by dt, and since r is a constant, circular motion radius is constant, so we can write this as dl by dt by r. But dl by dt is nothing but v, so v by r is omega. Similarly, alpha is equal to d omega by dt, which is a by r. So we get two very important results. V is equal to omega r and a is equal to alpha r. But keep in mind, since this a is d omega by dt, which comes from dv by dt, this a is the a tangential, and a radial we already know, that is v square by r, that is omega square r. And one final thing, I gave you the magnitude of angular velocity as d theta by dt. What is the direction of angular velocity? So the direction of angular variables are decided by the right hand rule. For example, if this is the direction of circular motion given by the arrow, then we curl our fingers in this direction, our thumb points towards the viewer, that is towards me. So the direction of theta, omega and alpha, all three of them are towards me. Instead, if I was going in the other direction, in this direction, then my thumb would point away from me when I curl towards the arrow, and then theta, omega and alpha would be away from me. We could have theta, omega and alpha, either one of them could be positive or negative, the equations would still be valid. So this finishes the kinematics of circular motion. After Newton's laws of motion, we will delve into the dynamics of circular motion, which will deal with the forces needed to produce these motions. Thank you.